Hey, hello everyone. So today we're going to talk a very interesting topic in stereochemistry. Okay. So before we go ahead, let's talk about the stereochemistry in a little bit brief manner. So it will be helpful in the further. Okay. So when you talk about the stereoisomers, okay, what is the stereoisomers when you can't talk about? The stereoisomers is a present in the compounds having the same chemical formula but different orientation of the atoms. So we know that in organic chemistry, or we can say in stereochemistry, the stereoisomers are of two types. First type is called diastomers, where they show the different spatial configuration. That's correct. Okay. And the unique characteristic of diastomers is what? They are non-mirror image of each other. Okay. That is the first most important point. But in case of after the diamonds, the stereoisomers are divided into or classified into enantiomers. And today we are focusing on this topic, that is enantiomer. So what are the enantiomers? They also show or exhibit a property of different spatial arrangement. Okay, arrangement, or we can say configuration. That is very important word over here, spatial arrangement. But rather than we can say they are non-mirror, they will be the mirror image of each other. And once they mirror image of each other, they are non-superimposable. Superimposable. So what is non-superimposable? So let's take example of that. Suppose this is your hand, okay, and this is a mirror image. This is a mirror image. When you put this on the same type, they are superimposable each other. When between talk about is non-superimposable as well. This is a thing, and this is a mirror image, we can say. When you put this, they are non-superimposable on each other. So that's the point over here, right? So let's focus on the enantiomer in detailed manner. Okay. So when you talk about the enantiomers, they are what? Same atom. Okay. Same arrangement should be there. No, there is a different spatial arrangement should be there. Okay, so let's talk about that in detailed manner. Now, before I go ahead, I want to draw a single line. Suppose I'm taking a red color and I'm drawing a line here. This is a part 1 and this is a part 2. Can you see that? Yellow molecule representing the yellow, exactly on the position of red, exactly of the blue color is on that position, and exactly green color molecule on there. So don't you think that they are equal distance from each other? Okay, when you talk about the mirror image, right? So that's a mirror image of each other. Okay, now the point is that enantiomers or what? Different spatial arrangement should be there. So how come they have a different arrangement? Okay, first of all, they are the mirror image of each other. That's the point. Okay, now when I'm trying to impose this molecule, means this first molecule, and I'm putting the second molecule in first, I'm getting the different things, right? Different scenario. Okay, so in this case, what is happening? Let's see here. Okay, see here. Now I want to show you something. So we are talking about what? We are talking about a very important point over here, that is in a coordination component. What? In a coordination compound. We are talking about the geometry. Okay, this structure is going to resemble a MABCD structure. So what is that? So this is a metal, obviously at the center. Okay, and is going to show the squarer planar. Why squarer planar? See, look at here. 1, 2, 3, and 4. So it's covering the all the square. So if the metal is at the center, this is H, this is H, this is H, and this is H side. So it is going to show a square planar geometry, right? Yes, a square planar geometry is showing. So when you draw the structure, you're getting here A, Here is B, here is C, and here is a D structure. Okay, so this is which type of coordination compound geometry? Square planar, that just we have discussed. But in this case, what we are talking about in a very detailed manner, type is what? MABCD or MABCD. Okay, so how many ligands are there? What is ligands? I use the word ligands over here. Okay, I use the word ligands here. What are the ligands? See, this is M stands for metal, which is here. Okay, and this A, B, C, D, the bonding which is going to form. Okay, they are called the ligands. Okay, so metal is forming bond with this. It's called the A, B, C, D. We are talking about this bond is called the ligands. Okay, so in coordination compound, this bond is called the ligands. See, if there is a bond between this metal and this, suppose this is A. Okay, so then what should I do that? I have to draw the bond. So this bond is called the ligand. Okay, are you understanding this concept? Yes, that is very, very important concept over here. Okay, so this bond is called the ligands that we just have understood. Now, see, I'm showing you something. I'm rotating here and there. So just understand, I'm changing the plane. See, now this is in this plane. These yellow molecules are outwards. Okay, if I'm putting this, the blue is coming outwards, the plane. Okay, and red we talk about, if I'm putting like this. Okay, so don't you think so? This is going to show you square and planet. Okay, so suppose I'm doing, let me erase this. Okay, these dots right now in front of you. Okay, these are the different molecules. Now at the center there is a metal. Okay, so metal is going to form a bond from this, then this, and this, and this. If you draw this structure or point, you get a square. Here the square is not properly drawn because the distance is there, but actually it's going to show you the structure. Metal is at the center and it's formed bond at the edges of the square, right? So that's why it's called a square planar geometry, right? So this is how. So are you understanding what is the square planar geometry? Every point is getting touch over here, right? That's the point. So see, now let's form the bond. This is the first bond, okay, which is at the edge. Then this is a green bond, okay, observe that. Then this is a red bond and this is a blue bond, right? Now, as I mentioned over here, what we have mentioned, enantiomers are what? They have different spatial configuration. That's correct. They are mirror image of each other. So how we can draw the mirror image? That's the point right now. Okay, this is a mirror right now. The line showing the mirror. See, exactly on this, I have to take one molecule. Exactly on this, I have to take another molecule. Exactly in front of this blue, I have to take another molecule. And exactly on the green, I have to take the another molecule. Okay, so can you see 1, 2, 3, and 4? Exactly, I'm taking the molecules over there. Okay, so when you join this, obviously you get the same diagram. Same diagram means what? Mirror image. So how the mirror image is going to happen? I'm changing the direction of this right now. Okay, now if I'm doing this, okay, that means exactly the green color. See, can you see the green color dot over here? Here, exactly beneath the green color dot is there. I mean, that represent the molecule. Okay, now next point which I'm going to draw, let's see here, then yellow, exactly the way I told you. Then there is a bonding. I have drawn the bond. Then green bond is drawn. I have drawn here. Then there is a blue color bond. I mean, blue color bond means it's going to represent the three bonding right now: yellow, green, and red. Now, what is remaining? Red. So exactly in front of that, red will be there. See? Yes, exactly. That's called is the mirror image. And exactly at the center, metal is there. That's why it's called the mirror image. Now, you understood? I hope you understood that now this is a mirror image. Exactly. We are talking about the mirror image of each other. Correct. So I hope you understood this point very clearly. Okay. So this is very, very important point. Now we're talking about a geometrical isomer. The geometrical isomers are what? GI, geometrical isomers. So how many geometrical isomers can be drawn in case of M, A, B, C, D? Okay. So there are different ligands. See, if you draw the square planar, metal at the center, here is a A, here is a B, here is a C, and here is a D. Okay, geometrical isomers, they totally depend on the distance, right? That we have know in the stereochemistry, right? And they have a constant rotation. But here right now, we're talking about how many geometrical isomers can be drawn of this enantiomers. So let's talk about this. So in this case, M, A, B, C, D enantiomers, let's draw that. Suppose this is M. See, I'm going to show you by the linear arrangement, then I will show you on the structure. So this is metal at the center that we have to draw. Obviously, metal has to be in center. This is A, this is B, this is C, this is D, right? This is the first structure. See what is isomers? Isomers means same molecular formula but different structure, right? So let's talk about a different structure. This is the first structure. Now let's consider this A fixedly point at the A, and I am rotating it clockwise. So A will be as it is. So if I draw the next structure, M will be at the center. A will be as it is. A will be what? As it is. Now I'm moving what? See, as I'm rotating this clockwise, so B will become in case of C. Okay, so C here will become B. See, because I'm rotating clockwise, right? I'm rotating like this direction. Correct. So this has become B. Here it become C, and here it will become D. This is the second structure. Again, I'm keeping a molecule or a atom at the fixed position. I'm rotating into the clockwise. So again, metal is at the center. A will be at a fixed position because we are fixing it, right? And so what is going to happen now? Instead of C, there is a B. Again, I'm rotating, so D will come into the picture. So D, B, and here the C will be there. So there is a bond between A and D, A and C, and A and B. All the three pairs are formed, right? The three pairs are formed. So this is a third structure. And again, I'm rotating clockwise. I'm going to get the same structure first one. Why? See, if I'm rotating taking the C again here, I'm going to get the first structure. Isn't it correct? What I said just right now, you can just have a look over there. Yes, exactly. So how many structures I'm getting here? Total 3 structures. Okay. See, look at the structure. Here is A, D trans, A and C trans, not trans, A and C opposite, A and B opposite. Okay. So you know the geometrical isomers consist of two forms, trans and cis, right? So here A is keeping fixed in front of their D is there. Then second structure A is fixed, C is there in front of that A. Then A is kept constant as a fixed as we're doing earlier, and we keep taking a B. After the third, I'm getting the first one. The same structure, that means I'm getting only the 3 structure. So this is called a geometrical isomers over here. Okay, are you getting my point? Now we know that the 3 structures are there, correct, and they are going to show the square planar again. So with the help of these structures we're talking about, let's talk about the first structure. I'm talking about the first structure here. So this is A, this is B, this is C, and this is D. If I'm rotating anti-clockwise, I'm going to show that. So what is going to happen? A is a fixed. A has to be fixed over here. So what is going to rotate? Is B has to be come into the place of what? C, A, B, C, D. This is a D, right? So B has to become here. Okay, C has to be moved here and D has to become here. So D has to become here, B will be here, and C, what is going to happen? C will be here, right? So don't you think so? We are getting the next structure. So have you understood clockwise structure? Okay, I will show you this once again here. Okay, so let me clear all the things and let's draw it now. This is A, this is B, this is C and D. Okay, I'm keeping A as a fixed point. I'm keeping what? A as a fixed point. When I'm keeping A as a fixed point, what's going to happen over here? It becomes the fix over here. So I'm rotating clockwise. What is the rotation? Clockwise rotation. So when you rotate it clockwise, okay, what's going to happen? B will be coming here, D will be moving here, and C will be here. Isn't it? Again, I'm going to rotate it. What's going to happen? A as it is. I'm drawing the structure right here. Okay, what's going to happen? A will be as it is, right? Then if I'm rotating again What's going to happen? C will become here, B will come here, and D will become here. Again, I'm rotating. I'm going to get the same structure as it is. Correct. So this is the rotation we have seen over these structures. Okay, I hope you understood every point that we have discussed. So let's just have a recap what we have discussed. We started with stereochemistry, then we talk about the enantiomers. They have a different spatial arrangement. These are the mirror image of each other, like yellow follow the yellow, blue follow the follow, in front of that red is red. So they are mirror image. As they are mirror image of each other, that's why they are called enantiomers. And then we talk about the MABCD enantiomer, where they are going to show the square planar geometry. And after that, we talk about the how many geometrical isomers can be shown by MABCD structure or type. Okay, so 3 geometrical isomers, and we just talk about the rotation clockwise. So we have just covered all the 3 points in the 3D structures. Okay, so I hope you understood that. Okay, thank you for paying attention.